My talk is about sister algebras of constructed called product systems. And before I start with what happens with the free abelian semigroup case, I have to go through what happens with the one variable case and with sister correspondences. So apologies for people that already know this. I'm going to go a little bit fast. So XA will denote a right module over sister algebra A, along with inner product that takes values in A. If you don't want to use this, you may think of X and A inside some B of H, the same B of H, A acts on the right on X, and you want this identity to, this inclusion to hold. Because you have an inner product, you have a notion of adjointable operators, that is module operators on X that admit an adjoint, and they automatically are bounded. And in there, you have a nice ideal, that of the compact operators, which basically is the same thing with what compact operators are for Hilbert spaces. So a basic example of a right module is a Hilbert space where A is, of course, complex numbers. If you want to think of this as in an algebraic way, you may want to think the compact operators as the set of all elements of the linear span of X star. And we'll say that X is a sister correspondence. So AXA will denote right Hilbert A module along with a left action given by A. And you have a homomorphs from A into the adjointable operators. There is a nice way to quantize this. So you can build a Fock space by taking the tensor products of X with itself, modulo the module A. And you can define a representation on A by acting on the left on elementary tensors of this form. So what it does is that for any element in A, you just act on the left and on the first factor. And for every xi in X, you define the left creation operator that just adds xi tensor to what it says. You also get for free a representation of the compact operators that does what you would like to do. The rank one operator xi eta, it takes it to t xi t eta star. Now, because you have a representation that preserves the inner product, the system algebra generated by pi and t, sorry, it should be overlined here and here, is actually a linear span of monomials of this form. So you take a bunch of xi's and then the stars of a bunch of etas. And back 98, Pimsley realized that this construct can contains a subclass several examples. And you can show that this specific sister algebra is universal with respect to all representations of AXA. In an analogy with the topological algebra of finite geometry. And an additional feature of the representations is the gauge action. It is something that Michael Brown mentioned Tuesday, I think. So you say that the representation pi t admits a gauge action if it leaves pi of a the same element-wise and it just multiplies by z any element from X. Why is that important? Then you can show that a pair pi t defines faithful representation of t of X if and only if it admits a gauge action and it satisfies the relation. There is no way that you can see A acting in the picture of the compacts. Now this bears the question. This bears a nice question. So one can ask, what is the smallest quotient of this T of X, such that whenever you have a representation of the module that is injective on A and admits a gauge action, then it leads automatically to a faithful representation of the quotient. And that's something that would be a Kunz type sister algebra, and Katsura wants to provide the algebraic characterization of this fact along with the existence of this co-universal algebra. And what you do is you take the quotient of T of X by these kind of relations where you have pi of A minus psi of phi X of A, where A is acting by a compact, but also lives in the annihilator of the kernel of the left action. That is the smallest quotient, a covariant quotient of Tx that you can take and still can preserve information, the complete anisometric information from A and X. Examples of this OX can be given by graph sister algebras, the well-known graph sister algebras, or the Z cross product So that is a nice machinery that extends this. The characterization by Katsura allowed us to have more insight and understand what happens with OX. So there is a bunch of nice results that I've put in this slide that you can have. So Katsura showed that OX is exact if and only if A is exact, and it's nuclear if and only if the embedding of A in OX is nuclear, which is good to know. And along these lines, he also provided, by also using the Kunz picture of the K-theory, he provided information on the K-theory. What I really like is this 6-term sort of exact sequence for the K-theory of OX, where one has to use the K-theory of Katsura's ideal and A. If you're familiar with the Z cross products, you can see here that this is exactly similar to what happens with the K-theory of the cross product. If you're familiar with graph system algebras, this is exactly what happens with this X0, this X1 is what comes from the adjacency matrix. It's a little bit technical to go through these details, but you do get the information here that you want. Further results that he has is a characterization of the T equivariant ideals. Now you have pairs of ideals to characterize the T equivariant ideals of T of X. The pair consists of one ideal in A that represents the kernel of the morphisms of A inside the T equivariant quotient, along with a picture of A inside the picture of the compacts. So this is why you have two ideals for these T equivariant ideals. Schweizer, back in 2000, he gave a nice characterization for simplicity of OX, so which really looks with what we know for classical case of the Z cross product. So OX simply if and only if X minimal and periodic, and I have the definitions here. However, this is mostly, I would say, corrected by Carlsen-Kwasniewski-Ortega, who gave a nice characterization of simplicity without having adjectivity or fullness for the cross product. So OX simply if and only if X minimal and quasi-nilpotent. And then in 2016, Brown-Tikuisis-Zelenberg provided a nice theorem that says that if I build a sister algebra from classifiable blocks with amenable in an amenable way, then I expect to have something that's classifiable. So properties of A do pass to properties of OX in this nice way. Of course, you need X to be, not of course, you need some finiteness in order to tackle finite nuclear dimension, and you need a Rocklin dimension property, but this passes through. This is some of the things that we know for one variable case, and for the free abelian semigroup. So for Z plus n, capital N, there is an analogous construct that allows you also to have commuting actions, for example. So a product system will be a family of xn's, so that whenever I write this n, whenever I compose it into a sum of the generators, when I write it in this form, there is one way that I can identify it with a nice tensor product along these coefficients. We also need compact alignment in the sense that whenever you have compact operators of some degree, then they induce adjoinable operators to a larger degree, and whenever you have an n and an m, you take their union, and you want the induced operators to still, the product of the induced operators to still be in the compacts. There is a universal sister algebra again built on the Fock space by using a left regular representation or by left creation operators. And Carlsen-Kwasniewski-Ortega provided a nice characterization for the co-universal object. It's a little bit more complicated, and it relies on checking some polynomial equations along the compacts. And I will come back to this point later, but what we want to keep from that is that we really know the co-universal object. An example to see is whenever you have xn to be regular means that being injective and acting by compacts, then this co-universal object is being Katsura co-universal along every fiber, which is something you expect. But if it's not regular, then things become a little bit more complicated. And their description here is that complicated because of this. The Artin back in 2007 suggested a decomposition of this higher rank, let's say, sister algebras by seeing them into successive iterations of the sister correspondence machinery. So if you had if you have a product system on two fibers, then you produce the tensor algebra, the topic algebra of one, and then you see this as a new sister correspondence over another sister algebra, and you produce the Topli's algebra of both of them. And Fletcher visited these iterations for general quasi-lattices. This is very helpful because it gives us, it allows us to pass some results from the one variable case to the multi-variable case. So for example, we know that because of the work of Fletcher, that the embedding of A inside NTX induces the isomorphs of the K groups. We know that if this is exact or nuclear, if and only if A is exact or nuclear. And also he showed that whenever X is regular, then NOX is exact if and only if A is exact, and NOX is nuclear if A is nuclear. Last year or a couple of years ago, I was interested in that question and in analogy to what Katsura does. And the result now that we can achieve without using the decomposition is that we can show that NOX is exact if and only if A is exact. Okay, this is not something really difficult. But what requires a little bit more effort is to show that NOX is nuclear if and only if the embedding of A in NOX is nuclear. Actually, you can do slightly more things. You can have item 2 here for any equivariant quotient between NTX and OX. And actually, you can also do it not just for product systems over Z plus N, but also for other quasi-lattices that are controlled by Z plus N and satisfy minimality property. Examples are the right-angled Artin monoids, if you want. Now, going back to, this required a little bit more machinery than what Katsura had, but the ideas are a little bit similar. You go and you check what happens with the fixed point algebra and how you embed A in the fixed point algebra. Let me go back a little bit to the characterization of the covariant relations. So Katsura for the one variable case has a nice description of the covariant relations based on an ideal in A. Carlsen-Kwasniewski-Ortega and Vidadello have a nice characterization, but now you don't see anymore one ideal in A or several ideas in A where these covariant relations come from. And Senem in 2019 produced a very general result and a very general construct for other quasi-lattices. However, what I'm interested into, when you go back to the one variable case, you see that this description with an ideal in A is very convenient for proving results. It's extremely convenient and allowed us to do a lot of things. So I was asking, okay, can we do something similar for the free abelian semigroup? Can we relate the covariant relations for this object to ideals in A? Unfortunately, you cannot do it for all of them, for all product systems, but you can do it for a bunch of them. So with Adam Doron, we took a look at what we call the strong compactly aligned product systems. These product systems have the additional property that whenever you have a compact and you induce this compact to something that is that adds one orthogonal fiber, you are still in the compact. Okay. Examples come from product systems where the actions are by compacts, or when every xi is of finite rank, or for product systems come from dynamical systems, or from row finite graphs. And not all high rank graphs satisfy this property. The row finite graph satisfied, and here item 3 is the characterization of when a high rank graph, a finitely aligned high rank graph, is strong compactly aligned, which I'm not going to go through it because whenever you have high rank graphs, you go to a lot of practicalities and technicalities, but it's there. There is an example, I just put an example of a non-row finite high-rank graph that is still strong compactly aligned. So here you have multiple edges, and there is an example where a high-rank graph is not strong compactly aligned. The problem is that the problem lies here at this source V. The problem is the following: whenever you have an edge E colored, let's say red, and for this E you have multiple solid arrows with which it interacts. You have countably many, and you would like to have finitely many. That's the only point. So in order to achieve a characterization of NOx, with Adam we took two steps. The first step was to have something similar to Katsura's ideal for the multivariable case. And what you do is you have to check all possible directions. So for any set of directions in the free semigroup, you take all the the kernels of this direction, you take the intersection, the annihilator, and then you check how many of them act by compacts. That's the first step. But it's not the only thing that you need. You need one more thing. You need to take also the biggest ideal in this JF, which we call IF, that stays invariant under the orthogonal action, like under the action of all the fibers that are orthogonal to it. And this comes because you need to solve some nice polynomial equations. The theorem that we have is that whenever you have a strong compactly aligned product system, we can have the covariant relations subject to this ideals IF. And they have a very nice description by taking alternating sums of their actions along these directions. The additional thing here is that we can see exactly the ideal of the covariant relations. And this is generated actually by taking pi of A wherever I is an IF. You hit with a projection that kills those directions in F, and then you take all the things that you can generate. So you can write it in a nice linear span form. The motivation came from a work that we did with K. Davis and Dan Fuller for dynamical systems, and I have the description here. And there is also a nice application we have with Adam for the strong compactly aligned high-rank graphs. The benefit is that you don't need to check all exhaustive sets. Okay, you need to check all possible sets of directions, but then you write them in a more compact way by taking products of this form. And there is some kind of resemblance between dynamical systems, high-rank dynamical systems, high-rank graphs. Just a note for people that are into equilibrium states. I'm not going to give definitions, but these nice projections, the QFs projections and the ideals that they generate whenever you take all of them, allows you to define what's called subharmonic parts. And one thing that you can show is that whenever you start with a product system of finite rank, then you can use this picture and these projections to show that you can decompose, you can have a whole decomposition into subharmonic parts. And even more, whenever you restrict yourself to the gates invariant equilibrium states, you can have a parameterization with a nice subsimplex in the tracial states of A. That allows you to determine two nice temperatures, one above which you have just K-M states of finite rank or classical states, and this comes from a notion of entropy. And one more that allows you, that tells you what is the lowest inverse temperature that you can go, below which you don't have any K-M states. And putting everything together, of course, in specific examples, you get more things. So for example, for all finite high-rank graphs, you can have a full picture, and combined with the work of Christensen, you can understand the KMS splices and find the phase transitions of the equilibrium states. Let me finish with some remarks. Actually, this is work in progress. So the first question is, can you have a description of the covariant ideals for the strong compactly aligned product systems? And the answer is yes, but in this case, you need to have one ideal for every vertex of the hypercube plus one for A, and this gives you two n ideals. If you put n equals 1, you get two ideals as you were expecting from Katsura's picture. With Francisca Ricci, we are working on connecting the K theory of NOx with that of X and A, and by taking these alternating sums, actually we can see these obstruction homomorphisms that Barlach has seen in the Z2 cross products. Further things are how to link the nuclear dimension of A and NTX, so that at the end the goal is to show that when you start with a classifiable A, applying something that's amenable by Z plus N, you get a classifiable NOx. And that perhaps will help us to bring even more sister algebras into the classification problem. So I will stop here. I want to thank you and just put some references at the end.